Hello, hello. How's it going? Ooh, 4 people joining us. Whoop, whoop. Welcome to the Linear Digression Show. I'm really excited about this. We are, David and I are going to be basically like going back and forth, sharing knowledge and just talking about data science type stuff for you all. And how kind of it relates to Timescale and how we are using Timescale to do some data science stuff, fun stuff. So yeah, today, super pumped. We have David talking to us about some more of our hyperfunctions and the statsag in particular.
Yeah.
So please.
So and just so folks know, I think the plan is for us to do an ongoing series of these sorts of data science-y topics over the next few weeks at least. If you are either here or like want to make it to another one or just have things that you'd like us to cover, please do let us know. Just for some background, I am a senior software engineer or something like that. My role is a little bit undefined at Timescale. I've been on a lot of different teams. Right now, I'm mostly working with the Toolkit team, and also spending some time doing some education work with the developer relations team. I've been with Timescale for almost 4 years now, so I'm one of the older hands, as they say. And yeah, I don't know, Miranda, maybe you want to introduce yourself too, so that people know a little bit more about us.
Yeah, no, that's a good call. I always forget that. Also, hello to those who are saying hello.
And yeah,
because I noticed I can't reply in LinkedIn, so I apologize. Yeah, so my name is Miranda All, and I am, unlike David, I'm very new to the team. So my background is in theoretical mathematics, actually, and data science, kind of in the data science world after school. And so this is my first year with Timescale. I'm about almost 6 months here. I absolutely love it, by the way. So if you are looking, shameless plug, if you're looking to join a really, really awesome company and team, Timescale is really, really awesome. Just a really great environment and community. So definitely encourage anyone that is interested. Yeah, it's awesome. So yeah, I am a developer advocate for Timescale. And so I kind of take all the awesome work that David's team and our other team does. And I feel like we have the very unfair job of just getting to showcase how awesome everything is and play around with it and just kind of test things. So yeah, I feel like I have a very fun job as a developer advocate. Yeah. So that's me.
cool. Yeah, so I'll start off. If you want to share my screen now, I can start going into some of the statistical aggregate stuff. Cool. So yeah, so we're going to start off. I don't know how many folks were at our community day the other day. I'm going to start off with basically the same example as we went through there. So sorry if it's review for some folks, it's probably new for others. And then we're going to go and delve a little bit deeper into some of the cases that we were looking at there. So yeah, the example is basically we're an ops team. We're for an online store. We have like a microservices architecture or something like that, and we're monitoring APIs for performance. And so we have a table that looks something like this, right? It's called response times. It has an API ID. It has a timestamp, and then it has the time that whatever API it was took to respond to the user. So that's obviously something that we're going to care about a lot as the ops team, because that's sort of measuring what's actually like the end result of what we care about. Maybe there are also some internal APIs Those things we also care about. Different APIs might have different times that that we sort of expect responses in, etc. So one of the things that we want to look at is, okay, if we have a lot of raw data here, this is not very easy to see what's going on in a graph. So one thing we might do to solve that is do some statistical downsampling. So the standard way that we might do that would be to take the average and the standard deviation, the sample standard deviation in this case, using the normal Postgres functions. And we could plot that, and that looks a little bit nicer. I'm also going to go over, so we have introduced some slightly different ways of basically writing that same thing. So these two things are the same. So we have average of statsag of response time is the same as average of response time, and standard dev samp of response time is the same as standard dev of statsag of response time. And you can also get the population standard deviation if you just add in the population parameter there. That's no problem. So part of what I'm going to talk about is why we have this sort of two-step approach. So we're going to go over some aggregate stuff there.
Sorry,
yeah.
just to recap. So this one that you're showing right here is the timescale functions, right? As opposed to the last.
This is the Timescale Toolkit statsag functions, and we'll show a little bit more about why we did it this way, where you do the statsag and then you do the operation on the statistical aggregate. We'll also talk a little bit about potentially what's in that aggregate if you want to. So either way, we're going to get a 1 minute downsample. And as I was going through this the other day, we said, okay, well, that looks a little bit better. I can understand this a little bit more. By the way, on this graph, the blue line here is the average, and the gray line that we're graphing is the standard deviation, basically added in each direction. It's not a great way, really, of representing an API response time, because as you can see, we're going negative, but it's something, it works reasonably well. It gives us some more information. So maybe it would be better if we did a 5 minute downsample. Okay, we can do the same sort of query with a 5 minute time bucket instead of a 1 minute time bucket. And we see that that gives us a little bit more, like, our graph is a little less crazy and hard to read. We see that there's this thing going on around 6 o'clock, 1800 hours. Right, and so maybe if we went further, it would be more clear. And the thing is now, and so we go to 30 minute downsampling, but the thing is that this is now getting a little chunky, and that's a little bit hard. We don't really want to go that not fine grained, whatever the coarse grained in our downsampling here. And so one thing we could do is we could do instead and I should have changed the name of this, apologies, a windowed aggregate. So this is sort of the standard way that you would do a windowed aggregate in Postgres, in normal Postgres. So you take the average of response time, and we're going to do it over the last 30 minutes, right? And the thing about this, just so we're clear, is now we are getting a point for every value of response time averaged over the last 30 minutes with all the other points that were in there. And the standard deviation, the sample standard deviation over the last 30 minutes, again, for each point that we have. That's how the window function works here. So this window function says we're ordering by timestamp, and we're doing it over the last 30 minutes. So range 30 minutes preceding. Now, what I'm going to show you is how to do so this is what that looks like, by the way. But we're also going to show you how you can do that using our statsag with a continuous aggregate. And what that means is now we get really, it's more of a tumbling window, because we're getting it every minute. Because that's one of the things that sort of is weird here, is if I try and take the average before I do this, I have trouble doing a rolling window as well. So I would have to write that in a weird way if I wanted to get a rolling window with also on a minutely basis rather than at the raw data sample. So I'm going to switch actually over to the Jupyter notebook that I used so I can show you some of this stuff. So this is the Jupyter notebook that I used to make this. We've got some plotting stuff going on in each of these things. So this is our rolling 30-minute window.
Ooh, is there any way to zoom in a little bit just so we can see the text a little bit better? Because if you're like me, I like to.
Is that better?
See everything. Yeah, that's better. Yeah.
So this is our this is API 32 still. That's just this where clause here. We're doing an average over the last 30 minutes still, and we're looking at the non-materialized rolling average. And we're going to get a plot that looks something like this, right? We have the average, we have the standard deviation. We're using Plotly for all the plotting, by the way. Plotly is great. Really enjoying using it. And that works pretty nicely for this. But you'll notice that there's a lot of points. So this takes 2.5 seconds to run for 2 reasons. One, it has to go and get the data, and then it has to plot all that data. And there's a fair number of points in here. I don't know exactly how many, but it's in the thousands, multiple thousands, probably tens of thousands. And so that's something that you should just know. Now, what I can't do with this very easily is take the average, say, and then take another average or take the standard deviation. There's no way to get a tumbling window aggregate in a nice way. So the tumbling window aggregate we can do, though, with our materialized view that we mentioned over there, where we created basically using StatsAg, we create a materialized view, and we say, so the materialized view definition, let me actually just pull that up.
That was going to be my next question. Let's see that continuous aggregate or materialized view, I guess.
Where are you?
Because, right, you said this is a materialized view, not a continuous aggregate.
Sorry, this is a continuous aggregate.
Okay, so it is a continuous
aggregate. Yes, it's a create materialized view with
our special sauce.
Yeah. Okay. So, and I'll do that actually, by the way. So I will show you what it looks like. We can do both of those. So you could get out our original stuff from it. So here is that definition. So it's, let me make that a little bigger. So here that is. Is that big enough, or should I go a little bigger?
It looks, yeah, that's good to me. Yeah, for me.
So we have a create materialized view statement. It's called response times 1 min. We're going to select the API ID. We're going to time bucket it by 1 minute. And then we're going to do StatsAg. We did a percentile ag just for the heck of it, just to see it. And then we also have the average and the standard deviation, because we'll use those later. But basically, you're just going to use the inner call when
did you see the question, David?
Yes, I just saw. So
Awesome.
Roberto asks whether the code here that I'm demonstrating is published in a repository to facilitate the follow-up. So no, not yet, but I'm happy to publish this. Basically, I can just take, I think actually I made last time, and I can do this time as well. I'll just make a gist with the IPython notebook that I used, so you can take a look at it. And I can add in fact, I'll do it right now. And we'll just add this as a comment, just so we see. So, and
awesome.
Oops.
Yeah, great question. Keep the questions coming. Any questions that you have, please ask them.
So this is,
oh yes,
we will add it into the YouTube description.
Yep, we will add a link.
So yeah, so here's the continuous aggregate definition that we're basically using here. For now, we're just going to use the StatsAg part of this. It doesn't really change much, especially because it's not the largest amount of data anyway. But so, okay, so when we graph this, we get a very similar graph to the one that we had up here. It's like a very similar type of thing. We have fewer points, so it's like slightly less, it's a tumbling window now. We just have a point a minute rather than points, tens of thousands of points. There's about 1,000 points total. It's because it's not a whole day, but it's a good chunk of a day, and so we get 1 per minute here. And you can see that you can hardly tell the difference between these two, honestly. So this is a really nice way of graphing the same thing. And you'll also notice, by the way, that the execution time on this is much quicker. Once I click on it, it disappears. But we'll do that again and just see. So
and just reiterate again the difference between like those two that you had just run. One was using
so this one here is going from this one above that's a little slower is going from the raw data. And it's going from the raw data and computing a windowed aggregate just over using the average and the standard stuff from Postgres, average and standard deviation sample, and over the last 30 minutes. So that's how you would do that there. And then this one is doing it from our continuous aggregate. And so there we're getting 800 milliseconds versus 2.5 seconds. So that's nice. That's a difference. It's not a huge difference.
It's decent.
I want to show you, but the thing is that API 32 or whatever it was, 32, API 32 like isn't a huge one. Yes, the first example is only using Postgres features. The second one is using also Toolkit and Timescale DB features. So hyperfunctions along with continuous aggregates. So here, now we have the same thing, and the only thing that we've changed, this is the same as the first query. That is correct, Raj. You asked this, if you've understood, the first example is only using Postgres features, whereas the second is using tumbling window and continuous aggregates, and that is exactly right. So the first one is, and we're going to do this again now, and I just want to show you one where we have a lot more data, and so suddenly this is taking a lot longer time. And so API 8 has hundreds of thousands of points in this period, and it takes 50 seconds. Of course, as soon as I click on it, it disappears. But
I did see it. I can vouch for you.
Rather than the other one, which actually takes almost exactly the same amount of time as the first one.
That's pretty sweet.
So one of the things that you can get when you're using continuous aggregates in order to materialize some of this sort of stuff is predictable response times that are going to be relatively consistent, especially when you're doing things like tumbling windowed aggregates, et cetera, no matter how much the underlying data might change. And so it's a great thing to use when you're trying to enable dashboarding, et cetera, that you want to be consistent and quick. So this sort of query now, let's just take a quick look at, say, the explain plans of this. So in this is the standard window aggregate from Postgres. And this is the timing on it. So it's taking 28 seconds.
Pure Postgres. Got it.
Yeah, so this is pure Postgres. This is this query here, right? The one here. In fact, I'll run it and it will eventually, it skips down to the next thing, but in a minute or so, you'll see the response on this. It is currently running. So that's that one. And then we can compare that to the continuous aggregate one. So first off, you'll note that it's taking 28 seconds. And not only that, but it is actually, so first off, the window ag is taking a long time. It's also using parallel workers here. So it's actually using up even more server resources, though not for a huge amount of time. But that's just a thing to note. So, but part of the problem here is that it's outputting 158,000 points. which is just way too many. Way more than we can graph. So that's another reason that the tumbling window aggregate is something that people use quite often in this type of scenario. Now, so let's look at the explain plan for the continuous aggregates one. So we're down from 28 seconds to 3 milliseconds.
That's awful.
In terms of our response times. And that's the sort of thing that you can get. And I ran these several times. This is not just caching. And by the way, the other part of this is like, there's going to be some set overhead for just like network communication and graphing anything. So, you know, you can figure that it's going to take 500 milliseconds just to like do all of this stuff. So some of the time here is spent doing that. And let's see, did this finish? So this took a minute to respond this time. So, and that's figure it's probably around 28 seconds to run the query. And then it's gonna maybe a little bit more, maybe it's 30, 35, whatever. Depending on, you know, just random noise on the server. And then we also have the time that it takes to graph all of the extra points. So that's why we're taking almost a minute to graph this. Now your users are going to leave if you take a minute to graph any of this sort of stuff. And if I run this, right, it is, and of course it always skips ahead, but it takes less than a second to get what looks almost exactly like the same graph. So that's the basic gist of what's going on here and some of the ways that you can use StatsAg. And one of the ways that we really wanted to provide is just this idea of being able to use statistical aggregates in window functions with tumbling windows and getting the right answer. So let's go over a couple more things here. So first off, we want to see, and I chose a different API ID because it showed this a little bit more clearly. So I just the average of the average. And the answer is like, you'll get something that is close, but it won't be exactly the same as the actual average, right? And this is because there are different numbers of points inside of each bucket. And you can certainly figure out certain types of data sets will have more problems with this or less problems with this. But that's one thing. The other thing is calculating standard deviation. I certainly can't take the standard deviation of standard deviations. That's not going to make any sense at all. The standard deviation of the standard deviation, I think, is always just going to be 0 because there's only going to be one value per bucket or something like that. Or I guess it's going to be over a thing. So like, yeah, but you're just really not measuring what you want to measure. If you do something like the standard deviation of the standard deviations, it just doesn't make any sense. I guess the standard deviation averages, but again, that's not really capturing what we want to capture here. It's capturing just something completely different. And that's a really valid thing to want, by the way. You might want the average of averages. You might want the standard deviation averages. And that's totally fine. But it should be clear that's what you want. And there should be a way of getting the other thing. And so that's why we wanted to use this StatsAg, so that you can enable this rolling stuff, so that you can always just get the thing that you want, and it's going to be accurate. So let's look at some of that. So this is a graph of, and in this case, what we did is we did the average of averages.
Oh, and David,
average. Yep.
Do you want to just like do you want to explain real quick like how kind of the rolling works and why, like,
sure,
just like real quick, just, you know.
Yeah, so let me go into a few things. So let's go back to the presentation for a minute and let me explain aggregation quickly. So you may have seen some of these slides from before. I'm going to go through them really quickly. This is basically a graphical representation of how Postgres aggregation works. So we'll just go through some of those quickly. So this is an idea of the max aggregate. So whenever we have an aggregate in Postgres, the first thing that you should know is that we have some state and we have rows that the aggregate is scanning over and it's updating the state. So as we go through here, we have rows from some like with some value called bar, a row comes in, and the state gets updated. So if I'm looking for the max, well, okay, 2 is greater than 1, so now I update my state to be 2, and 3 is greater than 2, so now I update my state to be 3, and that's what's going on. Now this is called the transition function, or the state transition function, because it's basically saying, as I have my state, I have a row, okay, I need to do something to figure out what my next state is. And that's basically how the aggregate works. So an average, right, in order to really do that right, we need the sum and we need the count. So as I do this, now I'm going to update my sum and count. So 1 and there's one value and it was 1, so 1 to the 1. And then we have 3 and we have 2 values in there. And then we have a sum of 6 and our count is 3. So, okay, but I can't just output 6 and 3, right? When the user asks for the average, I need to do something with that. And the answer is I'm going to apply a final function here, and I'm going to divide 6 by 3 in order to get the average. So that's what's going on internally, is it does a transition function, it does a final function, and we get a result. Okay. So, and in pseudocode, you could represent it like this. So you could say the next state is the transition function applied to the current state and the current value. And the final function is the final function applied to the result is the final function applied to the final state. Now, a couple things to note here. One is that the transition function is the expensive part because it has to run for every row, right? Whereas the final function is relatively cheap. It's called for every group. So I might have to call the transition function 10,000 times or 1,000,000 times and only call the final function once. So if we parallelize it, one way to sort of change how the costliness of this is to parallelize the transition function. So in one place, I can do the transition function. Or in one instance, I can do a transition function for some set of rows, and in another instance, I can do the transition function for the other set of rows. So as I'm doing this, you can see that each of them updates, and the transition function is correct for each of them, and they're processing their set of rows. And so then the next thing, as you got it, is, well, we need some way of then combining 2 different states, and that is the combine function. So the transition function is made to take a state and a new value and return a new state. The final function returns a result from the final state, but neither of those actually works on 2 partial states necessarily. Sometimes the transition function and the combine function are the same. For max, for instance, it would be the same. But for average, you need to be able to say, for average, you're going to add the sums and add the counts rather than count the counts, which would just give you 2 or something, right? Like that wouldn't be useful. You need to add the counts. So it's a little bit of a different thing than if we were just applying the transition function. Okay. So that's what happens here. Like our combine function will run as the partial states from each instance get passed to the main process. And then the final function will run on the output of the combine function. And the other thing that you should know, by the way, is that we also do deduplication here. So again, remember the transition function is expensive. So if we have average bar and average bar divided by 2, we'll only run average bar once, which is great. And so that's the basic lowdown on aggregates. Now, so
if I were to just like, because just to sum it all up, essentially, like the transition function is kind of like we're doing all the heavy lifting, and so that would parallel with the stats ag function that you showed in the code earlier. That's kind of like that heavy lifting function that we're doing with all the rows calculations. And then whenever we actually want to take the timescale average or standard deviation, that's the final function being applied onto the stats_ag or like this transition, equivalent transition function. Is it?
Yes.
And then the roll up.
So exactly. So
like
in the code that we were looking at here, right? The stats_ag is the equivalent of the transition function. The average is the equivalent of the final function, and rolling or roll up. We also have roll up functions for a number of these, and they're mostly equivalent. We can go over exactly what's going on with them because it turns out there's some other stuff on aggregates, and maybe we'll do that on another day because we're already halfway through the session, and there's other stuff to get to. So rolling is basically like the combine function. So rolling produces another stats_ag, but it's the combined stats_ag. So if there are 30 of them for the most part in each of my windows, right? And so I will produce one 30-minute stats_ag that I can then extract the average and the standard deviation from. So average of average, though, is going to actually take the average over the final, what the final function has already been applied, right? And so you're not going to get the same result. And like I said, it works okay for average. So we can actually take a look at this graph, by the way. So we see that the average and the average of averages are rather different here, right? I mean, they follow the same general shape. You're going to get something that looks okay. But like I said, if you want any of the other statistical moments, then you're kind of SOL. And that's another thing, by the way, with the statistical aggregates that we have multiple things, multiple statistical moments as well. So you can compute the standard deviation. You can compute also the, and let's go into this. So we also, I won't go into actually for now anyway, the two-dimensional statistical aggregates. But so here you can see these are docs. You'll look under if you want to find this, you can look under API reference Hyperfunctions and go to stats_ag. There also, I think, are some how-tos on this, so that's another useful thing. And actually, maybe Miranda, you can talk a little bit about skewness and kurtosis. So standard deviation is the second statistical moment, and it's one that I think a lot of people learn about. So maybe you want to talk about that as well. But then we can also take a look at skewness and kurtosis, and then I can talk a little bit about how some of this stuff is actually calculated in the back end, but that might be for later. So Miranda.
Yeah. So if you had any like statistics classes, you probably talked about the normal distribution, and for just like a recap, it's like that classic bell curve, right? That classic bell curve. I'll try and center myself. So standard deviation kind of talks about how spread, it's kind of telling you like the spread of your data, how kind of far points might be from the mean or the average. And so kind of skewness and kurtosis are additional statistics that for many people, if you want to understand the spread of your data, the shape of the bell curve without actually, plotting all the points on the graph, you can use skewness and kurtosis to kind of get an idea for what the shape of your bell curve looks like. So skewness, which is the third standardized moment, that's like the very mathy statistical term. For most people, that doesn't really mean much. But essentially, skewness can be positive, negative, or zero. For a normal distribution, skewness is 0. And essentially, skewness is going to tell you, is the bell curve skewing, at all to one side? So is the tail, one side of the tail maybe skewed in the positive direction versus skewed in the negative direction? So that's kind of what skewness is telling you, is essentially if you were to take a normal distribution bell curve, right, and you were to skew. I'm trying to make sure that so let's say that this is the positive, since for you, I think as the viewers, this would be the positive. So if you were if I have the normal distribution and it is a positively skewed graph, then the tail on the positive end would be like, if I were to pull, it would be further than the negative tail would be. So it causes the bell curve to look kind of like it's leaning to one side or the other. So that's what
if you want
skewness
to
tells
share
you.
my screen again.
I think. Yeah, no
one.
problem. Oh, yes, perfect. Yes,
that
that does help. Thank you. So I don't have to like play charades over here. So essentially skew is going to tell you, right, where your tail is being skewed to, whether it's positive or negative, or if it's 0 and it's perfectly symmetric, right? A perfectly symmetric graph would have a skewness of 0. So then kurtosis tells you it's the 4th standardized moment. Just again, for, math, if you are familiar with standardized moments. So kurtosis is going to imply longer or shorter tails. What? I'm just looking at the comment. Pulls on ears sounds like. So essentially, kurtosis will tell you how long your tails are compared to kind of where the meat of the bell curve would be. And so it tells you kind of like, are there more outliers potentially in your graph? Is it more kind of potential values that are potentially could be outlying values? So it's telling you how kind of like long those tails will be. So it kind of causes the bell curve part of it to look maybe skinnier or fatter, depending on how kind of long those tails are. But it's actually focusing on the tail. It's not on like the pointiness of the graph. So that's good to know. But right, it's essentially telling you, again, more about the shape of the bell curve without having to graph your data and figure out what the shape is visually. You can get an idea with numbers. And so for kurtosis, depending on the kurtosis equation that you use, which there are different ones, which that's fun, the normal distribution will have a kurtosis value of 3, or it will have a kurtosis value of 0. So that's actually one of my questions, David, if you know it. Do we use, for the normal distribution, are we giving a kurtosis value of 3 or 0? Do you know?
I don't actually know. Good question.
Okay. No, I was thinking about that before our stream, and I was like, oh, I should ask that question. So we will get back to you on which one we use.
I do not remember on that one. So we'll have to look that up and probably add it to docs. So Raj, you asked, is StatSag returning only high order moments, or does it compute more statistical information? So it depends, is part of the answer. So StatSag mostly is computing higher order moments. We'll go over a little bit of that in a sec. You can also do a 2-dimensional StatSag. So StatSag has a 1D version, and that's where you're calling it on a single value. You can also do it with StatSag y, x. So you'll see something like this, StatSag val2, val1 in the docs here. Again, I'll make that bigger. So that's going to compute not only the higher order moments, but it'll also do linear regression, covariance, and like slope, intercept, covariance, etc. It also does have, by the way, you can also get things like sum of y, like sum of x. So when you do a 2-dimensional statistical aggregate, you can always get out the 1-dimensional statistics as well by doing average y or average x in order to get out the value that you want, whether the x or the y. One thing to note there is that it's always done as StatSag y, x, not StatSag x, y. And that's just because that's sort of the SQL way of doing this. It's the same way that Postgres does it and the way the SQL standard does it. So,
I would
That's
be
just how that
curious. So, Raj, you mentioned, like, does it compute more statistical information? If you have, like, if you look at the docs and if there are other statistical like values that you would be interested in computing, we would love to know. Like, if there are other things. I was the one that brought up skewness and kurtosis to the team because I use that when I want to like look quickly, understand data really fast. So if you have things that you want to know, tell us. We want to know. Yeah.
Yeah, and you can do that. You can file an issue in the Timescale DB Toolkit repo. Would be a great place to do that, or start a discussion there. The other thing that you might want to know, or might not, so all of these aggregates are done using an extended 𝗥𝗲𝗃 algorithm. So just so we know, like, essentially the way that the sort of textbook way of calculating something like standard deviation or variance for an aggregate like this would cause some troubles, because you would be keeping track of the square of like the sort of standard way that we do this. And actually, I think it's here. So the standard sort of textbook math of this is that you would keep the sum of x squared and also the sum of x, and basically take the average squared, and you can subtract one from the other. And that works okay, especially if you have fully accurate, some sort of essentially infinite precision arithmetic, or close to. There's not really infinite, but close enough. So that's fine. But the thing is that that's not going to work very well with floating point numbers, because x squared can get very big and you can end up with rounding errors if you're not careful. And so we use a modified algorithm, and it's basically, it's, as we said, it's the one from Youngs and Kramer, which is, I think it was a 1971 paper. So, you know, it's old stuff. It's been used all the time. It's what Postgres uses. So we're using the same sort of thing. We did just extend it a little bit to include kurtosis and skewness, so the third and fourth moments. But it's basically just using a recurrence relation that allows you to compute the, essentially the, it allows you to essentially compute this from the just the ongoing sum. So as you get a new point, you can compute a new value for your aggregate. So it's actually very commonly used in streaming algorithms and in other sorts of online statistical processing algorithms. Uses the Youngs and Kramer technique. It's also combinable, so it has a combinable form. And that's another nice little thing that you might want to know. And so that's, you know, just to, this is actually a different paper that shows how you can combine these, if I remember correctly. And there are a few other papers that extend them even further. So, you know, it's, I wish I could explain this stuff a little bit better, but this I actually thought, so this is actually the paper by 𝗔𝗯𝗲𝗃. And it's from 1976. Anyway, good paper. If you're interested in this stuff, take a look. And you can take a look at how they define the recurrence relation. It helped me understand sort of what was going on. But the basic gist is that we're computing this on a per item basis, because otherwise you would need to go through. So there's sort of two options. You either go through once and you compute the squares of each, which introduces double precision or floating point error of some sort, or you would have to do a two-pass algorithm where you compute the mean on the way on the first time through, and then you compute the each value minus the mean squared, which will reduce the numerical error, but causes other problems. So by basically, you can take the best of both worlds, and you actually take the value from each point and subtract the mean that I did before, and that allows you to minimize the error while also doing a one-pass algorithm, which is also very important. So that's the basic gist there.
Lots of fun.
So let's go through another.
Stuff.
Yeah, we can if people are interested, like we can prepare some more stuff on that if people want us to go into some of like the algorithmic details on that. But my understanding of it is fine, but not great in order to explain it to people right now. So I would need to like go over it a few more times, because I am a little while ago. And also, I'd want to know that people are really interested in that, because otherwise I think people might just fall asleep. So, so as we saw here, we can compute the average of averages. That's going to give us a bit of a different answer. We can also, by the way, take a look at, and I'll just do this in a separate query, you can get the actual rolling average like we talked about before for API 1, right? And we can plot that as well. And you can see that the tumbling window average really captures much better what's actually going on in the true average here. It's not perfect because you do have the 1 minute bucketing that's going on here. So there's going to be some, there's going to be some skew and some difference. But it gives you a much better approximation here. So that's about what I have. By the way, this is the underlying data for that. It's weird. Yeah, so I think that that's about what I wanted to go over here. What's going on? So, you know, we could get into more if people have questions. So each of these, by the way, so with the rolling ones, we could get into window functions and exactly what's going on under there if people want to. But I think we're close to time, and also I would love to leave some time for questions from Miranda or otherwise about some of this other stuff. So, yeah, any questions on statistical aggregates and what we can do with them?
We love questions from y'all first. Any other questions? We had some awesome questions today. Thank you for interacting with us. It's like it's the best when you all like give your thoughts and give input. Like, it's seriously awesome. So please keep doing it. And if you have not interacted or like, you know, ask questions, like we love it. We want to hear from you. Regarding approximate percentile. Yes.
Mm-hmm. Oh, wait a minute.
Yeah, we have.
So let's introduce the concept of, while Raj is typing a question here, we introduce the concept of approximate percentiles. So we also
can we only use
I'll answer that in a second. But just to show you, right now we have we're going back to our initial API 32, and we wanted to plot it with instead of using the standard deviation, maybe we want to plot the average, but we also want to plot the 10th and the 90th percentiles. And so you can't use percentiles in a we can go to our 1 minute one. And you can't use percentiles in a continuous aggregate because you can't use ordered set aggregates in there. This gives you a better sense of that. It's a little bit weird because it doesn't actually have that much data. So things get a little bit odd when you're starting to deal with small data sets. So this just gives us a graph of the 10th and 90th percentile, and you'll see that the difference there is that now we're only shading from 0 up to the 90th percentile rather than shading sort of into the negative, which our response time there could be. So it gives us a bit of a better approximation of the actual shape of our curve. We might be able to use something like skewness and kurtosis to also do something like that, or to modify how we draw our standard deviation in order to do that as well. There might be other ways that we want to do that. So just a thing to note. In terms of algorithms, so Raj asked regarding approximate percentile, can we only use UDD sketch, or are there other algorithms? And the answer there is there are other algorithms for approximate percentiles. So if we go to percentile approximation, you'll see advanced aggregation methods. It looks like we need to actually add a table of contents here so you can get to UDD sketch and t-digest a little more easily. But they're over here on the left. So we have two different aggregation methods. The default one, as you noted, Raj, is UDD sketch. But we also have a t-digest method. And so that's a little bit harder to use, and it works a little bit differently. Like there's the possibility that it gives you different results, not necessarily better or worse, but definitely different than if you computed the t-digest on the overall thing. If you do roll-up or rolling with it, I think I actually only have roll-up for this. So if you do roll up with a t-digest, you might get slightly different results there, and that's just one thing to know about it. But it can be very nice for all sorts of, for a number of different cases, and especially for more advanced users who already know about some of these algorithms and have one that they're looking for. We're missing also, again, other than UDD sketch or t-digest that you wanted as a percentile approximation algorithm, please do let us know, and we will absolutely consider implementing it, especially if there's more demand from the community. So if you file an issue on Timescale Toolkit, that's a great place to sort of ask for that sort of stuff. Any other questions about this or other topics we can go over?
That was a great question.
Yeah.
By the way. Anything else? Cool. Yeah, that's a cool thing about our hyperfunctions is I really like that you can kind of play around with what kind of the heavy lifting function is. That we have some leeway there, which is really cool.
Yeah. Yeah, and the other thing about that is that you can actually we also have UDD sketch as an advanced method here, because we have a number of different parameters that you can then put into the UDD sketch algorithm. And our default one, percentile ag, doesn't, not at all, Raj, don't worry about bothering us at all.
More questions.
So in our default algorithm for UDD sketch, called percentile ag, right, you can't control any knobs, you just pass it a value. And that's because we've chosen a reasonable default for many different things. But if you want more control over that, even within the UDD sketch algorithm, you can go and provide a size and a max error as well as the value. So we wanted to both provide what we think is a sane default so that people can get started with percentile approximation, but then also allow people to play around with it and see what they can do in terms of, making the number of values they're storing smaller, or making it larger in certain cases, right? If you have daily aggregates and lots of data, you might want more than 200 buckets. You might want a few thousand, and that might, still be a heck of a lot less data than the millions or billions of data points that you had before. And you're happy to make that trade-off for the accuracy that you get otherwise. So there's a lot of different reasons why you might want to use a larger number of buckets or a different number of buckets. And so you can tune that with the more advanced algorithm there. Yeah. So yeah, I think that's about all the questions that we have and about all we have for today. I hope you enjoyed it. Please do provide feedback here or elsewhere. I'll also post a gist with some of the SQL and Python, like basically with the Jupyter notebook that I used. Obviously the data won't be there, but there will at least be some code for you to take a look at. And yeah, and then we can also get into some of the stuff at some point. So Just as a sort of, since we have 5 minutes in the hour left, I may as well just quickly go into it. So when we talked about some of the aggregates here, right, we said, okay, we have this combined function. So the way that the window aggregates work is not only do they have the transition function and the combined function, but they have inverse functions for both of those, at least in some cases. Not all window aggregates have it, but some do. So not only can you add a row, like when you're going through like this, and it'll show up in the transition functions and or in the combined functions, but you can also remove a row. So when a window function sort of moves over rows, it's processing some set of them, and you can actually see which rows are falling out of the back, as well as which rows are getting added in the front. And so the window function basically says, I'm also going to provide a way to subtract, to remove rows from my aggregate. And so what rolling does is it actually provides that as an inverse combined function in essence, or something like it, for statistical aggregates. It also has some checks for if we have too much of a change in terms of our values, because that can introduce error, then we're actually going to go back and recalculate from scratch so we don't introduce too much numerical error. So that's the basic gist there. I'm also happy to go over at some point some of the source code on this and sort of how this looks. All of this is in Rust. So I can go over what some of that looks like if people are interested in learning more about how the toolkit actually works in the internals. Both this is sort of the internal library that we use for doing the statistical aggregation, and then we also have the part of the library that defines the aggregates, etc. So like the create aggregate call for each of these, etc., as well as some of our how the actual aggregates are working in some of these cases. So that's stuff that I'm happy to do in a future one. But as you guys are watching this either live or in a future session, if you want to provide feedback on what you liked, what you didn't like, and what things we could do more of, like if you want to go over some of the code, please do let us know. I'm happy to go through some of that. So we're happy to sort of take requests as much as possible.
Yes. We want to do what you want us to do. Want to give you all good content that is as helpful as possible. Yeah, and as David said, I know that I'm really looking forward to also talking about the two-dimensional side of the stats ag and kind of seeing it in action. So I think that will be another later show or episode of linear digression. But yeah, please give us feedback. This will be posted on YouTube, and I will provide additionally all the links and the links that David talked about. Those will be in the description in the YouTube video. So if you have any questions on anything that was shared today, they will be in the YouTube video. So come back and check it out. Yeah, I think that's everything for today. In case unless anyone has any other questions. Last call? No? All right. Awesome. Thank you all so much for joining today. This has been really, really fun. And David, I love learning from you. And so this was super cool. So thank you so much for sharing your brain and time with us. Yes. Awesome.
Thanks for watching, Raj and Antoine and Roberto. Appreciate it.
Yeah. Oh, when is the next episode?
Yes.
We will be doing this. I'm finishing your sentence, Raj, and I hope that's okay. Oh, when will pipeline function be released? Okay, that's different.
Yeah, the pipeline function call and aggregates in the experimental schema with like the pipeline aggregate syntax. With now, it's only experimental stuff. All the pipeline stuff is experimental right now. I'm not sure when we're going to release it in full, My guess is we may stabilize some of the aggregate ending stuff before we stabilize all of the time vector stuff. Would just be a guess, but I'm not 100% sure on that. We're still, getting feedback from the community. So it would really help, Raj, if you want to try it out, just, work with the experimental schema for now. Help us find both the bugs and just like any usability problems. All of that stuff is really helpful for us. So please do, test that out. We're sort of waiting for some feedback and letting it bake a little bit before we completely stabilize it. So yeah.
Mm-hmm. Awesome. And just for a note, we are going to be doing this every Monday at 2. We'll have different sessions. Next week, I'll be covering some more beginner stuff on it's evaluating data and how you can evaluate data using Timescale DB and Postgres functionality. So that's kind of for probably more beginner or people kind of in the beginning stages of data analysis, or if you're curious on how to get started with data analytics from directly from the database as opposed to pulling it into Python or something else. So that will be what the session is next week. So definitely give us feedback. Come tell us what you want to hear. All right.
Cool. Cheers, guys.
Have a great day, everyone.
Thanks for coming.
Bye.